All right. First of all, I want to thank the conveners for organizing this fantastic session. And I want to thank everyone for being here right now. You know, the fact that we're still in this room means that we are the real scientists. And all right, so we are all here because we are interested in how machine learning and statistical method can be used to solve some of the challenging problems in polar regions. And today I want to talk about bridging Antarctic observations and models with deep learning. So the overarching goal of my research group is trying to bridge the gap between observations and models. Over the past few decades, we have continental-wide observations such as velocities, surface topography, bed topography, and satellite images. At the same time, we have physics models ranging from first principle equations such as the Stokes equations to sophisticated models such as the subglacial hydrology model. So the question I want to discuss today is whether we can use machine learning as a tool to bridge the gap between data and physics models. And today I want to share two stories that aim to bridge this gap. So the first one uses image segmentation to detect fracture patterns on Antarctic ice shelves. And the second one is a neural network constrained by physics equations. And this is the technique that was discussed in the previous two talks. So let's get started. So there's a wide range of fracture patterns on Antarctic ice shelves. And these are examples of the periodic patterns of cracks. So understanding the stability of cracks is important. And in order to validate physics models, we have to know where fractures form. And this is where deep learning technique is useful. So here I train a deep convolutional neural network, the UNet, to learn the fracture patterns from satellite imagery. So on the left is satellite imagery from MODIS, and on the right is the prediction of the neural network. So the grayscale denote the likelihood that the pixel contains fracture, and the white is the fracture location. So I want to point out that the UNet, there has been lots of successful applications of the UNet on other problems, such as the detection of calving front in both Greenland and Antarctica. And also earlier in the previous session, there was a great talk about how this can be generalized to detect continental-wide glacier terminus. So here we create a Google Colab. So if you are beginners and interested, you can find this link in my website and then train a neural network yourself. So once a neural network is trained, it can be used to predict fracture locations over all Antarctic ice shelves. And here, roughly 2 million pixels out of a total of 80 million pixels of ice shelf areas were identified as fractured, and they were marked in white color. So this fracture map serve as an observational benchmark and can be compared with a theoretical prediction. So here is a theoretical prediction of the parameter regimes required to activate fractures. And the vertical and horizontal axes depend on the thickness that is measurable, the stress, which is available from inversion technique, and the toughness that is available from experiments. So this gray area is the region where the theory where we expect to see fractures. And these points are the observations. So here we have about 2 million points, and each point represents the parameters calculated from the thickness, the stress, and the toughness at the fracture locations detected by the neural network. So here we see most of the points that the neural network detects as fractures fall into this gray triangle and is consistent with the theoretical regime that we expect. So this is promising because from such an approach, we can compare physics models with observations at a continental scale, and this would be otherwise challenging without a deep learning approach. So I want to point out that here we're just using a 125 meter resolution images. So there are certainly fractures that are too small to be visible. So moving forward, using higher resolution imagery such as Landsat and Worldview will be necessary to capture fractures at a finer scale and increase the resolution of the data model comparison. Okay, so now let's move on to the second part, a neural network constrained by physics equations. We know that when we train a machine learning model, we are essentially fitting some model to observational data. And we're trying to minimize some sort of loss function, which quantifies the difference between the ground truth from the data and a prediction from our machine learning model. However, if the data is noisy, it is very easy to overfit the noise in the data. So to illustrate this, here is a simple neural network. And a neural network is nothing more than a model of the output parameter y as a function of the input parameter x. So we have some training data y as a function of the x. And when we train a neural network to fit the observational data, the neural network find a prediction that minimized the cost function, which can be defined as the mean square error between the prediction and the training data. However, we know that our data is almost certainly noisy. So if we minimize the mean square error, we can easily overfit the noise in the data. And to address this problem, we can use physical principles to regularize the neural network predictions. So suppose the output y as a function of x now is governed by some physics equations. We can ask the neural network prediction to not only fit the training data, but also obey the equations that describe the data point. So in the loss function, we have the data loss that fit the observational point data, and we have the equation loss that guides the neural network to find a prediction that is consistent with the equations. And with this new loss function, we can avoid overfitting the data loss. We can make the predictions interpretable, and we can extrapolate the predictions beyond the training data points. So how do we calculate the equation loss exactly? Here, we are interested in some parameters as a function of space and time. So we use a neural network to approximate parameters of interest as a function of space and time. And when we calculate the equation loss, we substitute the neural network prediction into the equations and calculate the derivatives in the equations using automatic differentiation. So when the equation loss is 0, the neural network predictions satisfy the equations exactly. And I want to point out, because the neural network output are continuous and explicit functions of the input, so the derivatives of the output with respect to the input can be calculated exactly. And this overall framework is called the physics-informed neural network. It was initially proposed by Reitze in 2019. Okay, so we can ask some interesting questions, such as how to weigh the importance of the physics versus data. You can imagine if your data is noisy, then you might want to put more weight on the physics to regularize the neural network predictions. So Yuno Iwasaki is a student in my group, and she has been doing some systematic testing on the optimal way to weigh the data versus equation loss. And if you're interested, her poster is online, and we have a paper under review that's available online. So what do we do now? We know that many aspects of ice sheet modeling depends on the assumptions of ice rheology. And the commonly used rheology, the Glenn-Spool law, is based on laboratory measurement, which shows that stress increase with strain rate. And this relationship can be captured by a power law with a fitted exponent n equal to 3. But we know that the real glacial ice is much more complicated. In particular, this prefactor can depend on pressure, water content, impurities, and grain size, and it can be challenging to untangle their effect on the rheology. So earlier this year, and you have seen this a few times now, Melstan et al. Published this paper that utilized satellite observations to reassess the rheology of glacial ice. And they use velocity to calculate the strain rate and use the thickness to calculate the stress using this simple linear equation. And then they fit a power law to the strain rate and stress data and find that the stress exponent is closer to 4 for fast-flowing extensional regions. I want to point out that this linear simple equation is applicable to approximately one-dimensional flows. And here we are interested in the rheology in the buttressed ice shelf areas where the flow deviates from the simple 1D setting. So as Yang already pointed out, in these two-dimensional flow areas, there does not exist any simple explicit form to estimate the stress. So if we want to calculate, if we want to know the stress, we have to solve the two-dimensional shallow shelf equations. So here, Yangji Wang is a postdoc in my group, and he used a physics-informed neural network to solve the two-dimensional shallow shelf equations. I want to point out that the first application of physics-informed neural network to glaciology was performed by Brian Reel and for the context of basal mechanics inversion. And I encourage you to read this paper. Okay, so here Youngji used a physics-informed neural network to learn the velocity and thickness patterns that closely approximate the velocity and thickness data. And at the same time, we evaluate how closely do the neural network predictions satisfy the shallow shelf equations. So the mismatch between the neural network predictions with the equations and the observations will be used will be penalized and used to update the neural network parameters. So throughout the training iterations, the neural network will find the velocity, thickness, and viscosity fields that best describe the data and the equations. So in addition to fitting the velocity and thickness data, the neural network can predict a ice effective viscosity field. So this cannot be directly measured in the field. So the prediction, and because we don't have any training data for ice effective viscosity, the prediction of this effective viscosity is only possible because we involve physics during the training. So the outcome of this approach is a two-dimensional ice effective viscosity field. And if we substitute this back into the equations, we find that the equation residues are 2 orders of magnitude smaller than the individual terms in the equations. So the error of this inversion are small and quantifiable. And now we can ask all sorts of interesting questions, as already pointed out in Youngji's talk. We can relax the assumptions about a power law rheology, and we can examine under what conditions is power law rheology a good model. We can examine when is it okay to model fracture size with continuum descriptions with shallow shelf approximation. And we also find that if we relax the isotropic viscosity assumption, we can further reduce the equation residue. So this means we can use this approach to quantify which part of the ice shelves has non-isotropic viscosity. Okay, so I think this is exciting because usually when we think about physics-informed neural network, we think that you already have to know the physics, but here we can actually test the physics. We can test the assumptions that are commonly made in ice sheet models, such as power law rheology and isotropic viscosity. Okay, so to sum up, machine learning is a promising tool to help bridge the gap between data and our physical understanding of ice. And our physics knowledge is critical, and it can make machine learning models generalizable to beyond the training data. And importantly, these data-driven findings are empirical. So I believe it will be important moving forward to rationalize these data-driven findings to drive deeper and new scientific understanding. With that, I want to thank my group members and thank you.